Today we're going to take notes over more dimensional analysis. You'll need a calculator during these notes. You may remember we talked about the mole. A package of atoms or compounds that chemists use is called the mole. The mole is a really large number. It's often called Avogadro's number, and it's abbreviated 6.022 times 10 to the 23rd power. So a mole is 6.022 times 10 to the 23rd what? Well, it's that many things called representative particles. And typical representative particles could be atoms. They could be molecules if it's a covalent compound. They could just be compounds. That would be any kind of compound. Or they could be formula units, and those would be ionic compounds only. If you know the number of moles, then the number of atoms can be calculated. So, for instance, how many atoms are in 2.00 moles of aluminum? So we start with our train track, and the 2.00 is our given, 2.00 moles Al. So we have number, unit, and compound. We need to get rid of moles, so we have 1 mole on the bottom, and we have the number of representative particles in a mole on top. For an element, it's typically atoms unless the element is diatomic. So we have 6.022 times 10 to the 23rd atoms of aluminum on the top. Now in our calculator, we don't put in 6.022 and an X and a times or anything. In the calculator, we put in 2 times, and then we put in 6.022 EE23. Pushing the button that says EE takes the place of the times 10 to the power of part, and it's the way calculators are meant to be used with scientific notation. Never ever use the little caret, the little arrow that points up when you're doing a calculation like this. Some calculators don't say EE, they say EXP, and that stands for exponent, and they mean the exact same thing. We do our multiplication, the moles cancel, moles of aluminum cancel, and we end up with 1.20 times 10 to the 24th atoms of aluminum. Now notice that the first part of the scientific notation, 1.20, there are 3 significant figures there. And that's because our given has 3 significant figures. We can also do the opposite. How many moles is 9.03 times 10 to the 23rd atoms of K? So we start with our given, 9.03 times 10 to the 23rd atoms of K. We need to cancel those units, so we know that 1 mole of K is going to have 6.022 times 10 to the 23rd atoms. So we put the atoms on the bottom and the 1 mole on top. Now the atoms units cancel, and it leaves us with just moles. Our answer, with 3 significant figures, is 1.50 moles of K. Notice in both cases that we use 1 mole is equal to 6.022 times 10 to the 23rd. Whether the number 6.022 times 10 to the 23rd is on the top or bottom of the train tracks depends on what you start the problem with. Also, this can be done with any representative particles, not just atoms. The difference is the label. So we could use molecules, formula units, ions, pretty much anything. So let's review. A student measures out 12.0 grams of magnesium in lab. How many moles does this student have? So we start off with our 12.0 grams of magnesium, number, unit, and compound. We need to get rid of grams, so we're going to have to put the molar mass in grams on the bottom. The molar mass of magnesium on our periodic table is 23.305 grams per mole. 1 mole goes on top. Now our gram units cancel, and it leaves us with just moles. When we divide this number, we get a number that looks like this, 0.49372557. But notice that our given only has 3 significant figures, so we're going to have to round this to 3 significant figures. You might think 0.493, but 0.494 moles of magnesium. That last digit makes that 3 round up to a 4. Also, we can do the opposite. A student needs 2.30 moles of boron for an experiment. How many grams should the student measure out? So we start with our given, 2.30 moles of boron. We need to get rid of the moles unit, so we're going to put 1 mole of boron on the bottom, number, unit, and compound, and we need the molar mass of boron on the top. Our periodic table shows it's 10.812 grams per mole, so the 10.812 grams of boron goes on top. The units that cancel are the diagonals there, the moles of boron. It leaves us with grams of boron. Our calculator gives us this number, 24.8676, but we only have 3 significant figures. So we look at the first 3, 24.8, but wait, the 8 is followed by a 6, so it's going to have to round up to 24.9 grams of boron. So our previous work with representative particles and our molar masses work can now be put together. Suppose a student needs 2.6 times 10 to the 23rd atoms of fluorine for an experiment. How many grams of fluorine should the student measure out? We start with our train track and we put in our given, 2.60 times 10 to the 23rd atoms of fluorine. To get rid of atoms, we're going to need Avogadro's number on the bottom. So we have 6.022 times 10 to the 23rd atoms of fluorine, and that's equal to a mole of fluorine. But we're still not to grams. We need the molar mass. So we're going to put 1 mole of fluorine on the bottom, and the molar mass of fluorine, 18.998 grams of fluorine on top. So what cancels now? Well, it's several things. Atoms of fluorine on top cancels with atoms of fluorine on bottom. Moles of fluorine on top cancels with moles of fluorine on bottom. It leaves us with just grams of fluorine for our answer. So our answer, according to our calculator, is 8.202391231. Looks a bit excessive. If we look at our given, we have 3 significant figures showing, so we're going to have to round this to 8.20 grams of fluorine. Again, we can also do the opposite. If the student starts off with 56.7 grams of aluminum, how many atoms of aluminum does the student have? We'll start with our train track and put our given in the upper left corner, 56.7 grams of aluminum. To get rid of grams, we always need a molar mass. So we need the molar mass of aluminum on the bottom, 26.982 grams of aluminum per 1 mole of aluminum. Now we've got moles, we need to convert those into atoms. And we know Avogadro's number says that 1 mole of anything, including aluminum, is going to be equal to 6.022 times 10 to the 23rd atoms of aluminum. Now we have several things that cancel. Grams of aluminum cancels with grams of aluminum on the bottom. Moles of aluminum on top cancels with moles of aluminum on bottom. And it leaves us with just atoms of aluminum. We put our 56.7 into the calculator, divide by 26.982, and then multiply by 6.022 times 10 to the 23rd. Remember, it's 6.022 EE23. When we do that, we have this number, 1.265463 times 10 to the 24th. That has an excessive number of significant figures. We only need 3. So 1.26, but wait, the number after it's a 5, so we're going to have to round that up, and we end up with 1.27 times 10 to the 24th atoms of aluminum. Suppose you have 54.3 grams of cobalt-2 chloride. How many formula units? That's for an ionic compound. And how many atoms is this? So we've got two questions here. Let's look first at the formula units. We'll draw our train track and put our given, 54.3 grams of cobalt-2 chloride. Now, you have to get the formula in order to do this. Cobalt-2 chloride, that's not two cobalts, it's actually two chlorines, because cobalt-2, that's its charge, plus 2. Chlorine is minus 1, so we crisscross, so we get CoCl2. The next thing we need is the molar mass of cobalt-2 chloride. Because we're trying to get rid of grams, we need the gram molar mass on the bottom. From our periodic table, cobalt is 58.933 grams per mole, and we have two chlorines, which are 35.453 grams per mole. We add those together, we get 129.839 grams of cobalt-2 chloride per, and this goes on top, 1 mole of cobalt-2 chloride. Number, unit, compound. Always show them. It's a good habit to be in for when we move on in a couple of days and have more than one compound in our train track. So the grams will cancel with grams and we'll end up with moles. But we want formula units. Well, we know that 1 mole of anything, including cobalt-2 chloride, is going to be 6.022 times 10 to the 23rd formula units of cobalt-2 chloride. Feel free to use FU to abbreviate formula units. Now we see what cancels. Grams cancels with grams, and moles cancels with moles. It leaves us with formula units of cobalt-2 chloride. So when we do this, and we'll move this down to make room, we end up with this number on our calculator, 2.518462 times 10 to the 23rd. We're going to have to round this off to 3 significant figures, just like our given, so we end up with 2.52 times 10 to the 23rd formula units of cobalt-2 chloride. Now, how can we take that number and get it into our number of atoms? Let's take our number of formula units as our given. We're really just continuing our train track, but in this case, we're going to start over and put our given back here again. 2.52 times 10 to the 23rd formula units of cobalt-2 chloride. We know that one formula unit of cobalt-2 chloride has 3 atoms. Well, how do we know that? Well, we look at the formula and count the atoms. 1 cobalt and 2 chlorines. We had to do that anyway to get our formula, our molar mass for that formula. So we know there are 3 atoms in a formula unit. We could do this for a molecule too, or we could count ions. In this case, the formula units cancel and it leaves us with just atoms. So we essentially multiply our answer by 3 and we get 7.56 times 10 to the 23rd atoms. And that's not of anything, that's just atoms. So try these. What would be the representative particle of gold? Well, that's just an element. It's not diatomic like hydrogen or oxygen or nitrogen, so it's just atoms. How about nitrogen monoxide? Well, we see that there's mono in there, and anything that uses number prefixes is a covalent compound. Covalent compounds form molecules. For potassium bromide, we see that there's a metal and a nonmetal. That's an ionic compound. Ionic compounds don't form molecules, they form formula units. On your notes at the bottom, there's a couple of places for you to do these yourself. The question says, what is the mass in grams of 4.16 times 10 to the 23rd atoms of radium? See if you can work this out yourself and then check your answer. Your answer should be 156 grams of radium. Make sure that you set it up correctly and can get this answer. If you don't get this answer, you probably did something wrong. The next question says calculate the amount or number of atoms in 335 grams of aspirin. The formula is C9H8O4. Let's think about what we're going to need. We have the formula, so we're probably going to need the molar mass since we have grams as our given. The molar mass is 180.159. Make sure that when you add up your molar mass, that's what you get. Once we have formula units, or pardon me, molecules of aspirin, that's a covalent compound. Once we have molecules, we're going to have to convert that into atoms. We need to know how many atoms there are in a molecule of aspirin. For that, we can just add up the subscripts. 9 plus 8 plus 4. There are 21 atoms in a molecule of aspirin. Once you finish your calculation, see if you can get this answer. 2.35 times 10 to the 25th atoms, and that's your answer. They're not atoms of anything. They're atoms of carbon, hydrogen, and oxygen all together.